Can you hear me?
Hi, Daniel. Yes, I can hear you. Can you hear me? Or is it? Hmm.
Okay, good evening, everyone. We had our earlier. Okay, can you guys hear me now?
Yes, Daniel. I
Yes,
think
we
you're
can hear you. We can hear
Okay,
you.
thank you. Hi, everyone. Tonight, this evening, we're gathered again for the second section of the week 5 of the Break Data Analytics program. Nikita will be taking us through time series analysis in astronomy. I think we're at the top of the hour. So, Nikita, you can start, and then the other comment will be made after you finish this section.
Thanks, Daniel. So, hi, everyone. My name is Nikita Ramut, and I'm a postdoc researcher at South African Astronomical Observatory. And in today's tutorial, we will learn. Just a second. Oh, can you hear me?
Yes, we can.
Oh, okay. Thanks. There is some delay or something, right? Okay. Can you see my screen?
Oh, yes, Nikita. I think something is coming up, but it hasn't shown yet.
Oh, okay. I don't know if there is some network issue or something.
Okay. Maybe
Because
just
I feel like
you feel like
because I feel like there is some lag between. Yeah.
okay. There you go. We can see it.
You can see it, right?
Perfect.
Yeah. Okay. So in today's week, we will learn about time series data and like how to visualize it, how to plot the light curves, and how to how to analyze and find periods in these light curves. But before going into the basics of time series data, first we will talk about like how do we understand time. So in simple words, you see, time is a way, we measure the changes and events they are happening around us. So it's kind of a relative quantity. For example, we know that sun rises in the morning and then sets in the evening because we feel these changes. We somehow feel these changes, and that's the way we keep track of time. So UTC, which is the Universal Coordinated Time, and it is the time we all use for in the standard format. This is the globalized standard format for all time zones. Like right now, we are in a meeting, from different time zones, and it's because of like each country's local time is an offset from the universal coordinated time. And just for your information, this universal coordinated time is the time which is located at the 0 degree longitude, and the 0 degree longitude meridian, it passes through Greenwich, England, and it is the reference time basically for UTC, and all other times, like all other times in each country, is just an offset from this UTC. So, but in astronomy, we don't rely on this UTC UTC time format, and this is not our standard way of keeping track of time, and we usually use other unit, for example, Julian date, which I will explain later. And so here we will just talk about the Python libraries, which can be used for keeping track of everyday date and time, and it is essentially useful where you want to keep a track of logging observations, or like if you want to just calculate the duration between two time events, and which we can understand. So in this tutorial, so there will be three notebooks in this session, and the first notebook, which is the time Python, it will just give you a brief introduction about time formats in Python. Then we will cover time domain and time domain astronomy. And the third tutorial will be on time series data, how to analyze time series data in using Lightcup package of TESS, and which can be used for analyzing dataset from TESS, Kepler, and K2. So you see, okay, so now in this notebook, we are using Astropy. And I mean, sorry, we are not using Astropy. We will use that in the second tutorial. So in this, we are just using Python's inbuilt modules like date, time, and time to understand the time formats in Python. So here you see, we have just used the date time module from Python. And if you just call this module, and if you write date time now, and if you just run this cell, you will see it will give us something like this. So you see the output is the current local time, which is like in Cape Town right now, it's 11th June 2025, and the local time is 18:05 41.479 seconds. So you can also print the individual values, like if you just want to see the year or month or day, hour, minute, seconds, or even nanoseconds. So if you run this cell now, you will see that you will because we are in different time zones, so you might get a different time or maybe a different date if you run this cell now. Now we can use this date time module to create an an array of this, of any kind of time format. So here we have just used this date time module, and we are just using inside date time module, we are using date time, and we are specifying, okay, this is our year, then this is month, and this is date, and this is hour, minute, and second. This is also the date of the first detection of the gravitational wave event, which is GW150914. So in astronomy, so some of the nomenclatures are done by using, just using the date, month, and year format. So for example, here you can from this name GW150914, you can say that, okay, this event was observed on 14th of September in 2015. And you can use the print command to print this specific event date, which we have created just now using the datetime module of the Python library. And if you just want to rely only on date, and you are not interested in seeing the times, you can also create like just by using just date. Now we have not used time here, so you will see if I run this cell, you will see something like this, which is just saying that, okay, this event, so this specific event time which we have created is this, which is in hour, minute, and seconds, and this is just a date. Now you can also use this datetime module to, if you want to calculate the duration between the two time events. So suppose my time one is something like 15/11/2023 at 10 hours, 0 minute and 0 second. But let's say my second time is 15, 11, 20, 23, but it's now 10, 30 and 0 seconds, 10 hour, 30 minute and 0 second. So if you would like to see the difference between the two times or the duration between the two different time events, you can just do an arithmetic operation here. So we define our duration as time 2 minus time 1. And if we just print this duration, it will give us the value. And if you want to see this duration in minutes, you have to just define that, okay, duration, you have to just use this duration, but you have to define that it's, you have to call this function total seconds, and you have to convert from seconds to minute, you have to just divide it by 60, and you will see if I run this cell here. So this will tell us the time difference is 30 minutes and the duration is the duration in minutes is 30. You can also use the date time module to check whether a particular date, a specific date of your interest, whether that lies in a particular window or not. So let's suppose here my start window, I mean the initial window I'm interested in it starts at 9 hours. We are just using the same date here, and the end window goes up to like 11 hours. And so I want to check whether my time 1, which is this, whether this time 1 is within this window or not, the window which I have specified here. So because now I have 3 times, I mean the time 1, which I'm currently using here, and I have 2 windows. So if I just use, if I just ask something like that, just check whether this time 1 is in between these 2 windows or not. So because now you know that, okay, the start window is 9 and the end window ends at 11 hours, and our time 1 is at 10 hours. So it will provide me an answer with true. So it will so you can use these different I mean you can use the date time module to check whether any specific date lies within any specific window or not, or you can use that to create, I mean, if you want to compare different data set which have been observed in different time, times, so you can use this command just to, I mean, this module just to compare these all data set. Now, so till now our whatever we have used till now is just a simple, we have just created an event, and we have just stored that as a using datetime function. But if you, so now we are interested in creating a data frame where our columns, they contain a specific time stamp. So here, to use that function, we will use pandas, and we will convert these columns into a specific datetime format, so that it becomes, so that the arithmetic operations, they become quite easy to handle, and we can just use this key function, which is like PD to datetime, to convert our specific columns to consider as a timestamp format, to consider that, okay, this column is denotes time. So here we have created a simple data frame where it has like 3 columns. In the first column, we have specified that, okay, my event ID, whatever, it just like a serial number. So it's like the event IDs are 4, 1, 2, 3, 4, and the timestamp strings denotes the different times, these different timestamps, and these are the different 4 values corresponding to these time timestamp string. So it's similar to like, so it's somewhat similar to like, okay, so suppose you are interested in, you are interested in checking whether how much is the temperature changes from the morning time to the evening time. So suppose you have some kind of sensor with you and you are monitoring the air temperature of your city across a single day, and you use a sensor that records all the which records the temperature once every hour. So what will happen? You will get 24 temperature values and you will get 24 hour values. So you will have something like, let's say, in X label, you have something like hour, which is our time, and in the Y values, you will have the air temperature. So this thing is similar to what here you can consider that these timestamp string denotes to our hour in like in this our experiment of calculating the like weather calculating the temperature, and these values could denote the temperature here. So now we are interested in making a data frame which will consist of all these three parameters. So if I run this cell, you will see this is how my data frame will look like. So these are my event IDs, and these are the individual timestamp string, and these are the, and in the third column, you can see this is the value of corresponding to these individual timestamp string. But like, let's see what type of data type all these three columns denote. So you can see the event IDs are the integer type values, and the timestamp string, these are the object type values, and the value is again the integer type values. But now we can use this now we can use PD to, we are calling pandas and we are using the function to date time, so that we can convert this data type from object to a timestamp string, so that our we can do more time-like operations very easily. And it's also useful for if we want to do any arithmetic operations here, and so that we can also take advantage of our pandas time series feature. So now when we use this command, this function PD to date type date time, and now if we see, okay, if we see the data type, it will be date time 64, and then in the bracket there is something written which is ns. So now this ns corresponds to nanoseconds. So this also tells us that, okay, this also tells us that the timestamps which are here, they are stored with nanosecond precision, and it's also the smallest unit of time which is supported in pandas date time feature. So now we can use because now our data frame has this information that, okay, this is the date, and time information in the second column. So once we have this information, we can easily filter our data frame to select any row based on the specific date, time, or any time range. And we can also use any comparison operators, like if you want to check whether any event one, whether that event one is great, whether that event happened before or after any particular event. So here you see, so here we have the same data set, but now we have this timestamp string which denotes 4 different times and the corresponding y values. So suppose now we are interested that, okay, we only want to see those data points which occurred after 6th of January 2023. So what we have to do here, so we just define that, okay, this is my filter date. I only want to see those data points or those rows which either happened on this day or occurred after this particular day. So we can just use this operation which is greater than equal to here, and we can define or we can call our data frame, and we can call the timestamp string now, because we have defined our timestamp string as the in the datetime format. And we so because now it has the information that, okay, this specific timestamp string has all the essential values which represents our time here. So we can just call that, and it will just compare the values in this timestamp string, and if those values are greater and equal to with these values 6/1/2023, so it will just return us a data frame containing only those values where our timestamp strings is either 6th of January 2023 or later than that. So that is the reason you can only see 3 rows here. So this is essentially important when you want to see a specific event which might have happened a particular duration, which might have happened during a particular duration or during a particular event. And we can also use this filter. We can also use this timestamp string now to filter the events between 2 dates. So suppose here we were only interested in the initial date, but now we are interested in a range. So we have defined our starting range as this and the end range is this, and we are only interested in those data which have like only those events which might have happened between these 2 events. So you can see, because the in our original data frame, the time corresponding to 7/1/2023, the hour minute second is 11:00:00, and here our end range corresponds to 23:59:59. So this timestamp is obviously in between these 2 ranges. That's why it has returned us this data frame now. So this feature is really useful if you would like to filter your data set based on a particular event. So like in astronomy, if there is a long-term data, like you have multiple, so you are suppose there are multiple observers all around the world, and they are observing a particular target, and they started observing that target from the year 2021, and suppose they are still observing the target, but you only are interested in the data of the year 2025. So you can for that kind of analysis, you can just define your start range, and you can say, okay, end range could be today's date, and if you filter it like that, so you will be able to see your data set which only contains the rows that have been observed during 2025. So now, because in time series data, we have time which is like inherently sequential in time. So we can always we can always we can always set our column as the time as the data frames index to show that it contains the time information. So for that, now I will just run this cell and I will just say that, okay, this is my timestamp and this is the original data which we had earlier. And now if I use this command, which is the events df is our data frame, and if I use the set index command, so it will set the timestamp string as the index. So the point is that now I can use my timestamp string to call for any rows containing that value. So it's like if I use, so let's first see how does the data looks like. So you see the time now, our timestamp string has an index. So if I call my data frame as that I'm only interested in this value, so it will give me all the corresponding event ID and the corresponding Y value. So similar to the exercise which we recently did, like to filter your data based on the different time ranges. So now we can use this indexed data frame where we can just call that, okay, this is my initial date and this is my end date, and we can just use the events df indexed data frame now to slice our data using just the date of the data frame. I mean, we can just use the timestamp string and we can just call the individual days and we can filter our data in that way. So suppose we are interested in filtering our data for a specific day. So suppose we are interested in the data of 8th of January 2023. So here for that, we can just use the events df index. This is our new data frame, and we can just use a function .loc. So the loc, it ensures to select all the rows from a data frame based on its labels. So it will check like all the rows where the label is 8/1/2023, and it will return us all the rows where 8/1/2023 is in the timestamp string. So, but here, because we only had one entry for this event, so we have only got a single value here. So you can try making a new data frame based on the multiple entries for your date and time, and see how like if you use this index value and if you call the loc function, how does this change your data frame. So now this is the simple exercise in which like you learned about how we can use different types of time in Python, but now we will be interested in saying to use Astropy function because it handles that time format which astronomers generally use for their observations, and because of consistency, because we kind of use the same time format for our data. So you see, so first let's understand what is time domain. What does the time domain astronomy means? So whenever an astronomer observes any celestial target, it observes the target and measure its brightness or magnitude. So the time domain astronomy, it is that area of astronomy where we can where we observe the changes in the which are happening in the sky. So those changes, it could be change in those changes could be change in their position, or change in their brightness, or change in the spectral type. So there are many types of physical process due to which any celestial object shows any kind of variability, and some of their examples are pulsars, or even our nearest star, sun. It shows a 11 or 12 years solar cycle in which it's kind of magnetic. It is related to the magnetic activity which is happening in the sun. And there is another class, another class of transient events which we generally discuss in time domain astronomy. So these transient events are those events which they appear very suddenly, and they change their brightness very rapidly. And here rapidly means it could be days or months, or it could be a few years. And then the particular target, it fades away. So it's like it was there. So suppose there is a transient event. So let's suppose you observe it today, and you can see that, okay, the particular target is very bright in the sky. And if you observe it, let's say in 2026, you might not able to see that object there in the same position. And this type of transients include supernovae, gamma ray burst, or stellar flares. And so in this second notebook, we will learn about what a time series data is, and how do we measure these. How do we depict the light curve, and how do we analyze and how do we visualize these individual light curves. And we will use astropy.time module for the time presentation here. But before going on into that, so I will just discuss a few key terms which are generally used in time series astronomy, and when we use any kind of time series data. So as I have already explained, the time domain astronomy, it's that branch of astronomy that deals with the change of any physical property of a celestial object over time. And these objects could be transient events, or even the variable stars, or some kind of exoplanet activities, or some stellar flares, or galactic nuclei flares. And what is a light curve? So as I discussed, so when I told you that, okay, let's do an experiment and let's record the air temperature in every hour. So in that experiment, you had 24 data points, which were kind of representing your time, which the range for that time was from 0 to 24 hour, and you have corresponding y values. So a light curve is basically a plot between these two values. So in case of astronomy, we don't you can just replace the hour value for the you can use those hour values with the values which an astronomer has observed any kind of data, and you can exchange your air temperature value with the flux or magnitude of any astronomical object. So in this way, in a light curve, so basically a light curve is a graph in which in the x-axis you have time, and in the y-axis you have brightness. And so flux and magnitude, they are the interchangeable phenomena which we generally use to describe how bright or faint a target is. And a flux is just a physical measure of rate of energy which is coming from a celestial source per unit area, and magnitude is just a logarithmic scale to measure the apparent brightness of any object. And a variable star is a star whose brightness it varies. I mean, as the name suggests, its brightness or flux, it varies during an observation period, and that period, it could be hour scale or minute scale or year scale. So it depends on the type of that variable star or the physical phenomena which is going around that object. And an epoch, so epoch is just a specific point in time. I mean, okay, you can understand this from the example of the exoplanet or an eclipsing binary. So if there are two stars which are rotating around the common center of mass, so there would be a point where one star would be like, it will be eclipsed by the star which is just in front of that. So we can say that, okay, that particular time when the first star has eclipsed the second star, it is the epoch of eclipse. We can say that, okay, so that particular event, we can consider that, okay, that we can call that particular event is as an epoch. So it's like a very specific point in time and to show any special feature. Now, as I discussed that, we don't use UTC in observations, or I mean, we don't use UTC in while we create our time series data or while we plot our light curve. So the reason for this is that because so the astronomers, they observe all around the world. So if I'm observing from Cape Town and someone is observing from India or China, so they might have different, so we do have different local times, right? And we cannot just use those local times to say that, okay, at 1835 South African local time, this phenomena happened. We need to be in the same scale, in the same time zone to say that, okay, these two features might have happened at the same time. So for that, for consistency and conciseness, we use Julian date. So the other thing is that because our Earth is also rotating and orbiting around the sun, and because of that, the light which is coming from, so, and at the time when we see that light, it is shifted depending on like Earth's position in its orbit. So to correct for, we use barycentric Julian date, in which we shift all our time, all our observation time to a universal point. And this universal point is the barycenter of the solar system. So therefore we use barycentric Julian date, and therefore this is the reason that it is a globally accepted time scale that also corrects for the Earth's movement and also for a consistent time scale all around the world. So now in this tutorial, we will mostly use Astropy module, and it's astropy.time module because it handles this BGD time format, and also because we kind of interested in using BGD as our standard format. So, okay. One thing which I would like to add here that, okay, so BGD is the barycentric Julian date, but what is Julian date? So Julian date is a continuous count of days since noon time, I mean the noon universal time on January 1, 4713 BC. So because it's it starts at noon. So suppose you are observing in the evening, you are observing from 7 p.m. So you might have a local time of 7 p.m. And if you end your observation in the morning, then your local time would be 6 a.m. But if you see the universal coordinated time, so the date has changed during midnight. So now, because by definition our Julian date is the noon time of January 14713 BC. So it stays the same when we are observing. So that's one of the so that's kind of the main reason we like to stay in the same Julian date when we are observing, or when we are observing a target for a longer duration of time. So now we will just import all these libraries, and we will see how we can create a new data frame containing time using Astropy time module. Where is it? So see, here we have defined, so we have just used time module of Astropy. And okay, by the way, you can also, so there are multiple formats, multiple time formats which Astropy can support, and you can go through all the time formats using this link. So now we are interested in an observation time, which happened on 15th of November 2023 and 12 hours 0 minute and 0 seconds. So we can just use the time module, and we can define that, okay, this is my year, this is my month, this is my date, and this is hour, minute, and second. And we can just define, okay, now for now we are interested in the coordinated universal time, UTC. So if you just run this cell and if you print, so you will see it, the time information will tell you that, okay, so now time is 15th of November 2023. So suppose now, because as I said, we mainly work with JD. So let's see how we can define our time in a JD format. So it's not very, I mean, you are not doing anything extra here. All the things, the correction, the barycentric connection, even if we have to, whenever you have to do it, you can always use the time module for that, and you can just define your time here, and you can say that, okay, my format is now, my format is not UTC, it's I'm trying to see my observation time in JD. So this will give you the time in JD format. So you can see it's in JD, our time is, it's such a big number. So for conciseness, there is another date format, which is the modified Julian date. So there is just an offset between modified Julian date and Julian date. Since the modified Julian date, it started on November 17, 1858. So the same date, which was like in JD, which was 2460265, in MGD, it's 60264.5. So the modified Julian date, we sometimes use modified Julian date for conciseness, and because, so suppose you have data points, a large set of data points which started like the first point is from 2005, and the last entry is, let's say, from yesterday. So when you plot these data points, so you don't want to see such a big number in your x-axis. So you can just use an offset. You can just say that, okay, now I can use an offset. So your X label could be 60264. I mean, you can just subtract any offset from either from modified Julian rate or either from JD, and you can use that small number for better visualization and better presentation. So now the question arises, how can we convert between the different formats? So what you can do, you have to just use this dot ISO or dot MZD or dot JD format. And whatever format you use, you will be able to see that UTC time, the universal coordinated time, in different formats. So it's the same observation time which we have defined earlier. It's in MZD, and here it's in JD. Now suppose you want to do some arithmetic operations here. Suppose you are interested in, okay, let's add 1 day or something, anything to your observation time. So using this time module, you can just add whatever value you would like to add to your observation time, but you have to just define something here which is called a unit. So suppose you are interested in adding 1 day and 6 hours to your observation time. So you can define here that, okay, so this one is your day. So you can say that, okay, you can just say that, okay, the unit of this quantity is day here. And similarly, if you are interested in adding a 6 hour to your observation observation time, you can just define here as you can just define here that, okay, 6 is your value, but the value of the unit of this value is hour. So this will just give you your time, whatever observation time we defined earlier, and plus 1 day and 6 hours. I mean, the whole point of this exercise is just to show you that, okay, you can do arithmetic operations using the time module of Astropy. And if you are interested in the total duration of 2 events, so suppose some stellar flare happened on 1st of November 2022, and then the second flare happened on 30th of November 2023. So you're interested in seeing the duration between the two events. So for that, what you can do, so we already have our observation time here. You can define the time of your second event, which is this. And you can just subtract these two events, and you will see that the time difference here. But if you want to see the time difference in hours, so you have to define, you have to say that, okay, so this is the time difference, the value which we got from this arithmetic operation. But here you have to define that, okay, you want to see your result in the hour unit. So in this way, you just saw that it returns a value, and it says that, okay, the time difference in hours is 12 hours. Now you can also use this time module of Astropy to handle arrays of different time means. So it's similar to that experiment where we were recording the temperatures at particular hour of the day. So it's like you can define your time. So let's say it's in MJD. So we have defined a numpy array here, which has 3 values, 3 different time values. And now we have defined a time array. So it says that, okay, we have just used time module here, and we have just provided some basic information that, okay, the array which we just created here, which contains all our MJD values, and we are defining here that our format is MJD, and it will just return a time array in which our time is in MJD. You can do the same exercise for JD as well. Now, if you are interested in printing the individual value, or if you are particularly interested in a particular event, so you can say that, okay, I just want to print the first entry from this time array. So the first entry from this, so you might know that in terms of indexing, so whenever there is an array in Python, so this will be labeled as 0, and this will be labeled as 1, and this will be labeled as 2. So when I say that, okay, this is my first index, so it will return me the value corresponding to the second value in that array. So suppose I would like to see the first, let's suppose I'm interested in the first entry, so I can just change my index here and it will give me, so obviously this is because this was done for second, but this will say that, okay, this first time in this array entry is 60264.1 and the time in UTC is this. Now you might have become familiar with the Astropy time formats. So it's most of the times we deal with Julian date, and even when we are dealing with Julian date, we can supply an offset because we don't want to see these huge numbers, and we can see later that how we can use that offset. So as I discussed earlier, so a light curve is the very fundamental tool which is used to analyze the time series data in astronomy. So it's like you are observing a particular target for a longer duration, and you just want to see how its brightness or its flux changes over a course of duration. And you would also like to see whether the amplitude of that variability is changing, or whether the period is changing, or like what kind of features are present in a light curve. So in simple terminology, a light curve consists of a numpy array in which in one a two-dimensional numpy array in which we have time values in x-axis and the brightness or flux values in the y-axis. And we already discussed like how BZD is important in case of astronomical observations. And now we will see some common light curve examples, and they will be particularly, they will just let you know that how, on the visual, if you would like to see a particular light curve, how it looks like. So below we will see an Ogle light curve for a planetary microlensing event, Ogle 2019 BLG 1180. And this data we have taken from a published paper, which you can go through if you would like to read more about this event, of this particular microlensing event, and it's available in archive or in here in the journal website. So this event was observed with OGLE, which stands for Optical Gravitational Lensing Experiment. And this particular telescope, it's like they do long-running astronomical, so it's kind of long-running astronomical survey. They are mostly focused on detecting and studying exoplanet, variable star, dark matter, and they use gravitational microlensing method for their detection and characterization. So now here what will we do? We will use the special feature of Astropy, which is a table. So we will just use this feature to import tables from this publication, and we will also use AstroQuery So Astropy is a tool which we use to query astronomical database, which are online in different servers. So here we are using Vizier, but there are another servers like Simbad and NASA Exoplanet Archive or etc. So using the second line, this line, we are just importing the Vizier module to access the catalogs which are hosted on a Vizier database. And so all this, like whenever any paper is published, so if there are long tables, so that table, so whatever, if there is long table there, and that table can be like, they can be stored in these Vizier servers. So now, so whenever you whenever you go to their server, and if you would like to see like which type of data is available, or whether that particular target is in, if that target is available in any standard catalog, or whether there is any data for that object. So if you go to their server, so there is a row limit when you search for that, and it basically tells you that, okay, you can only see first 50 or first 100 rows of that table. But here we are using this command just to make sure that we can just to make sure that it returns all the available rows from that particular table or particular catalog. So as I said, here we will use that particular this particular paper, and this instance 0 means we are interested in the first table of that catalog. And this command will tell you that, okay, so for now we are only interested in seeing the first 5 entries. So if you run, if you call Vizier, and if you use get catalog and you just provide a reference there, so you will see that something like that, and it is like it is an Astropy table in which you can see this is telling you the information that, okay, the instrument with which the Glare observed the data, it's KMTA02, and these are the time formats, and these are the magnitude, and these are the associated errors. But this doesn't look very good, right? Because I said that, okay, we are now like in the process of seeing a light curve, but this table doesn't look like a light curve. You cannot just say whether this thing is variable or not just from this table. So what we are interested in, we are interested in plotting these values, like the time and their magnitude and the associated error. So here, okay. So this time format HJD, it is the so it stands for heliocentric Julian date, and it's somewhat similar to the barycentric Julian date, but the main difference is that in the barycentric Julian date, our assumption was that our reference frame is the barycenter of the solar system. Here it's heliocentric, which means that the center is, all the observation have been corrected to the considering that sun is at the center of the solar system. And there is there's not very much difference between HGD and BJD, but like people used to use HGD as a time format before, but nowadays we are more interested in using BJD only. So as I said, we are interested in plotting these values. So we have just defined an offset here. So as I said, the heliocentric Julian date, so whatever values are written here, these are this offset 2450000 plus all these values. So this is the offset which they have defined in their observations, and and we are interested in seeing how does this light curve, how we can interpret these values. So the JD offset is that, and we are just defining our x values as we are converting our these heliocentric Julian dates to we are also applying this JD offset here, and we are saying that, okay, consider all the values which have this, like which are in the, which has this title header of the header of HGD, and we are adding this JD offset here, and then we are subtracting this JD offset just to make sure that we don't want to these huge numbers in plotting. And these are the usual plotting commands which you might be familiar with now, because the matplotlib has been discussed, the matplot, how to use matplotlib and how to use these specific commands, how if you want to plot something with error bar, or if you just want to do scatter plot. So I'm hoping that you already are familiar with this. So, but for instance, so if we want to visualize our light curve with, where we would also like to plot the individual error values, so we just use, so the x values are the time values in our case, and the y values are the magnitude, and the y error is the associated magnitude with these y values. So if you run this cell, you will see a nice light curve, and you can see that this particular event, it is quite constant. You can say the variability is not too large, but between this region, you can see that there is a sudden rise in its brightness, then it like fades away, then it came back to its quiescent value, but then again it went up and it came down. So you can also see that the magnitude difference between these quiescence phase and these special brightening phase is almost about 1 to 1.5 magnitude. So now we will see another example of light curve. So it's this one is very special because it's the Sagittarius A, which is the center black hole of our galaxy Milky Way. So here we have used the infrared data at 4.5 micrometer from Spitzer Space Telescope, and the paper in which this data has been published is here, or you can also see the paper in archive. So this is the link to that paper, and here this just tells you that, okay, you are only interested in the first table on this paper. So if you just use this command, you will be able to see first 5 entries of the table. So here you see it's the MGD, and you have the individual flux values and the associated error. And because you cannot, as I said before, you cannot say anything just based on these values, whether this thing is variable or not, and how much is the variability. So for that, we will plot this table as well. And here we have defined our MGD offset as 56630, but you can also, write it as 56600 or 56636. But it just helps. For in very simple case, you can also just use the first, the integer value of the first theta point, like this 56636. So the offset we are using, it really doesn't help to do with the whole data set. It just has to be the first, just has to, it just, I mean, you can just use the first integer part of the first data point. I mean, the integer part of the first data point. So similarly, here we have defined our time values. So here we are using the time function of Astropy, and we are calling all the MJD values as our time, and we are defining that our format is in MJD. And here we have defined our X values to be like to apply this offset. And now, because we don't have here, we don't have the we don't have the errors here, so we will just use the scatter function for plotting. So we will just provide the X values, which are the time values, and the Sagittarius, these Sagittarius A values, because this is the keyword which we have in the header here. So when we call any entry with their like the header of the table, it will read all the entries which are here, like all the flux values. So if we just run this cell, where you will see a nice light curve of Sagittarius A in the infrared range. And you see here also the you can also see here that the system is somewhere at quiescence level around these range. But if you go here, so you can see the variability is very significant, and from like 0 value 0.001, it has gone up to 0.01. So that's a lot in the sense of the variability amplitude, and in terms of the variability duration as well. So till now we have seen optical and infrared light curve. Now, how whether if there is any change between the radio light curve or optical or an infrared light curve. So the light curve, basically, whenever we say light curve, it's just that we only have two information, time and the associated magnitude or flux. So in case of radio sources, I mean the source which emit in radio wavelengths, their physical process are quite different from the standard thermal emission which we see from the stars in optical wavelength. And the primary mechanism, these are quite different. So here we have synchrotron emission and the coherent emission. And if you would like to read more about these emission, you can just Google it or can go through any book which you would like to use. So, but I just would like to tell you that, okay, so the most of the synchrotron emission which we see is generally come from the systems which have strong magnetic field. So this kind of so the radio jets or the radio emission is generally seen in radio wavelengths where there is a strong magnetic field. And similarly, the jets which we see in active galactic nuclei or the supernova remnants. While because another process is coherent emission. So it's a process where particles emit radiation in phase with each other. So it's the same process which is responsible for the radio emission from pulsars, which are like the spinning neutron stars. So here's the thing in radio wavelength. So we don't measure here flux or magnitude. We measure the radio brightness in terms of the flux density, and the standard unit of the radio brightness is Jansky. And this Jansky means when 1 Jansky is equal to 10 to the power minus 26 watt per meter square per hertz. And here are some examples which emit in radio wavelength. As I said, these include pulsars, active galactic nuclei. I mean the jet. Most of the jet emission from active galactic nuclei, we see that jet emission in radio wavelengths, and the fast radio burst. So now we will see a radio light curve, which is also already published, and it's from this source J1402 plus 5347. And if you're interested in this particular target, and if you would like to see in detail, you can go through the paper at this link. It's already on archive. So here we will use the similar old stuff. We will call Vizier, and we will just use get catalog function. And this is the link to that paper. And also here also we are only interested in the first entry. And then this command will only print the first 5 entries of the table, which you can see here. So it's now you have JD values and the flux values. And we can, like, as we have done earlier, we can plot similarly to earlier plotting functions. We can also plot these values. So we will just apply an offset as we did earlier. And here we are only interested in scatter plot because we don't have any associated errors here. So if you run this cell, you see that this is the very interesting light curve of J1402 plus 5347. And you can see there are multiple variations across the whole observation. So you see it was at 0.005, it was showing the flux density of 0.005 here, but then it went up to 0.018, but then it came down, and the same features could be seen until 0.4, until 0.48. But here you see the variability amplitude is somewhat larger. And even in these events, you can see it has reached a maximum value of 0.35. So these fluctuations, these tell you that, okay, there might be the multiple periods which are present in this light curve, or the multiple physical processes due to which we are seeing the different kinds of variability. Now, the another example which we will see here is a variable star, which is known as RL Leo, and we have used light curve from SN catalog. This is the survey telescopes to detect supernovae or their remnants, and because it continuously monitors the whole sky, so it also gives you some detection on variable stars as well. So here we are reading this CSV file, which is already here, which is already uploaded to which we have already uploaded to this folder, and we are just using this CSV file, and we are using Pandas read CSV feature to read this file. And we are also filtering our data on the basis of the error in the magnitude. We are not interested in those data points which have larger error. So here we have defined that, okay, we are only interested in those data sets, those data points which have magnitude error less than 1. And similar to the earlier version of this, where we were just printing the first 5 entries. Here we can another thing is that we can also use this head command and hand function. So if you use this, you will see the first 5 entries of this CSV table. So here you can see the first column, it represents the heliocentric Julian day. The second one is the camera. So because there are multiple cameras in this survey. So you might have observations for a single target from different camera setup. So, but we are not interested in that part right now. And it also gives you magnitude and the associated magnitude error and the flux and the associated error in the flux. Now, if you use this command describe here, so it's such a nice function which you can use if you are interested in the statistics of your data. So it will just summarize the statistical properties of the columns in the data frame. So this tells you that, okay, the mean value of a GD is this, and I mean, let's talk about magnitude. So it just tells you that, okay, the mean value of magnitude is 16.09 and the standard deviation is 0.20 and the minimum magnitude which have been observed is 15.596 and the maximum is, let's say, 16.942. So this is a command which you can use when you are interested in the statistical properties of your data data set. So similar to the earlier cells, now we will just use the error bar command here, and because now we do have the associated errors, I mean the associated errors to the magnitudes or flux, whatever you want. I mean, you can plot whatever value you want to plot. So here we have just defined that, okay, the errors in magnitude is this, and this is our y value, which is magnitude, and this is the time value. And if you just run this cell, you will see a nice variable light curve of RLEO, and this just tells you that the source is quite variable because the faintest it has been observed is with a magnitude of 16.9 or something here, and the brightest it has been observed at a magnitude of 15.6. So this is how a light curve looks like. So whenever I say, okay, light curve, so light curve in astronomy, so it has to do with the time and magnitude. So till now in this tutorial, we understood that the different kinds of light curves in different wavelengths, but in the next notebook, we are only interested in the dataset from TESS, which stands for Transiting Exoplanet Survey Satellite, and we will see how can we find a periodic feature in a particular light curve. And so these are the additional resources which you can go and have a look. So I have already discussed most of the things here. So like what is a time series data and how a light curve looks like. But the main thing which we will understand here is how to identify periodic signals in the data and what is a periodogram technique and how can we use light curve as in light curve package and Astropy for Kepler or test data. So light curve is a special package which has been designed to work with test, Kepler or K2 data. And okay, these are the different kinds of, different kinds of celestial objects which show variability and which show a variable light curve. So one of the most famous ones are variable stars, which like they get brighter and they might get dimmer over a course of time. And if we just record their brightness every night, we get to know their time series data, and we can understand like what kind of variability of and what kind of periodic feature it can show. The second one is exoplanets. So exoplanets are the same thing, but I mean the same thing in the sense that so suppose there is a planet and it comes in front of a star. So it's the similar stuff as we discussed for the eclipsing binary stars. So if a planet comes in front of its star, so we will not see, I mean, it will block a small part of the light which is coming from the star. And you will see a tiny dip in that light curve. And by analyzing that dip and by analyzing whether the dip is real or not, we can discover new exoplanets in this manner. And pulsar, these are the spinning neutron stars, and they emit regular pulses. I mean the time scale of these pulses are in microsecond or even in nanoseconds. And supernova is the end stage of a star's life. So whenever a star explodes, it suddenly becomes very bright and then it fades away. So depending on the physical process responsible for the explosion of that star, the duration between the bright phase and the when it and the time when it fades away, it depends on that process. So in this tutorial, we are only interested in test data set, and we will be only using the Lightcup package to access the test data and to analyze the test data using Astropy time series function. And okay, so there are okay, so there are multiple. Let me just So there are multiple data products which are available in from TESS, and if you are interested in if you want to study in detail about these data products, you can go through the link which I have provided somewhere down. You can, I mean, I will just let you know about the link later. But basically, it provides two data sets. So first one is the Lightcup product, and it is just a table, an Astropy table, which contains the flux values and the corresponding observation time. But there is another value, there is another product file, which is the pixel file, and it is just a stack of images, and it just provides you the pixel level observation and the corresponding observation of time. And you can also create a light curve from these target pixel files. And but we are not interested in that part here. So we will just use the Lightcup products, and based on that, we will first search for light curves. So to search for light curves, you should have at least two information. You should either know your target name, or you should know the coordinate. So for coordinate, you can use the decimal format or the hexadecimal format. It doesn't matter, because TESS can search based on TESS can search for both the formats. So, and we can use the same keyword for Kepler or K2 data as well. And this identifier is the TESS input catalog identifier. And whenever TESS observes a star or any object, it provides a unique identifier. It assigns a unique identifier to that particular star. So in this tutorial, we are interested in an eclipsing binary, which is which is known as beta Persei, and the tick ID for this target is this, and we will use search light curve function here to actually search whether there is any data available for this target or not. So this LK is so because we have imported light curve as LK, so we can use the acronym here. So we are just calling light curve here, the light curve module, and inside that we are using this search light curve function, in which it takes a few keywords. So the first one is target, the second one is mission, and the third one is the author. So the mission, you can mention TESS, Kepler, or K2, and in the target you can mention the name or its coordinates, and the here author is SPOC, which is the pipeline which produce all the test data. So for test objects, you have to mention that, okay, this author is SPOC here. So now if you run this cell, you will see whether there is any data available for the target or not. So here you can see it contains, so here you can see the 4 data products. It is like, in this table, you can see the mission and the year in which the data has been observed, and the author because we specifically mentioned that we would like to see the test pipeline products. So here, the author is same, and this is the exposure time, which is 120 seconds or 20 seconds. So this test pipeline, it provides the final data with a cadence of 20 seconds or 120 seconds. And this is the target name, and this is the distance. This is the distance between the name which we have provided and the name which is in the test server. But here you can see there are multiple sectors. So how does test observe any field? So the test field of view is comprised of 24 degree into 96 degree. So it's so happened that whenever it observe a particular field, it shifts from that field and observe another field which is of the same reason, which is of the same size, 24 cross 96 degree. So that's the reason that the same star can be observed again and again, because TESS observes for 2 hours in northern hemisphere, then it scans the southern hemisphere for another 2 hours. And because it started, so the first TESS observation that happened in 2018 or 2019, something like that. So and if you see, so TESS has observed 2 years in the northern hemisphere. If we say that it started its first observation on 2018, and then it observed for another 2 years in southern hemisphere, and then it went back to the northern hemisphere. That's why you can see there are multiple sectors and the multiple observations of the same target. Now, we can also use the search light curve function to search for the target if we don't know its name, but we only know its coordinates. So it will give you the same result because there is no difference between whether you search it from coordinates or from its name. So you will see the same table here again. Now, if let's say I'm only interested in the first entry. I just want to see the first entry. So it will just pick up the first row and it will return me a table containing the information which is just for first row. Suppose you are interested in whether a particular target has been observed in a particular sector or not. So you can do that as well, but you just have to specify here that you are interested in sector 18. For instance, if we are interested in sector 18 data only, so we can define an additional keyword here, which is 18 here, and we have defined a new name for this search result. So we have just called it as search result 18, which dictates us that, okay, this is the search result for sector 18. So if you just run this cell, it will give you a single data product, because you know that when we when there was no restriction on the sector values, it provided you the data with the 4 sectors data, and we had like 18 second, we had data for 18 second, for 18 sector, then 50 and 85. Now, suppose we are interested in 85 sector data. So I can just change this value here, and irrespective of whether the data is available with 120 seconds or with 20 seconds, it will return both the values. So now here you can see that, because in sector 85 we had 20-second data and 120-second data as well. So this search result has returned 2 data progress here. But we will just, so for now we are only interested in sector 18 data. So I will just change this keyword again. Now, how to download the test light curve? If you know that now, because now you know that your target has been observed in this particular sector, and you already have a search result. So you can just call this search result function, and you can just write dot download here, and it will, and you can define this result as a light curve event. So you can just, if you just run this cell, it will give you a table in which you can see there is time, flux, the associated flux, and there's another thing, time correction, and we are not interested in this part, but I will just let you know that so this thing, so here we have multiple columns, but as you can see, it's something called SAP flux and the associated error, then the background and the associated background error. So to know more about these different values, you can go through this link. And also, if you are interested what kind of data products test provide, you can go through this link, and you will, the every detail is stored here. But for now, we are only interested in three values, which are time, flux, and error. So test provides 2 type of flux values, and one is known as the SAP flux, which is the simple aperture photometry flux, like the traditional photometry which we do for our target. So we define a region around our target, and we define an annulus region around our target, and consider that annulus region to be the background, and the small region which depends on the FWHM of our star, that defines the region for our target star. So this is the so the SCP flux is the traditional simple aperture photometry flux, but while there might be some instrumental systematics in the test data, and this PDC SAP flux, it corrects for that instrumentation systematics, and also if there is any nearby star, it also corrects for that contamination or contamination from the nearby star. So now, because we do have the data with us now, so we can plot this data and we can actually see how the data looks like. So before plotting them, we will just clean our light curve file. So we will just remove the NaN values from it, and so there might be some outliers. We will also remove them, and we will just plot the data points. The x-axis is time value, and the y-axis is the PDC step flux value. So if you plot this, if you run this cell, you see that this is the nice, interesting light curve of beta Persei. And from the literature, we already know that its period is 2.867 days. So you see, as I mentioned earlier, that this target is an eclipsing binary. So you see, this is the dip, the first dip, and this is the second dip of second dip in the light curve. So so the depth of the dip, it depends on the temperature and size of the two stars. So now, if you would like to save this data set, so what you can do, you can use Pandas, and you can save this clean data set into a data frame. So here what we are doing, so we are calling our cleaned light curve, and we are just using two Pandas function so that it can store, we can store these whatever values, whatever columns we would like to save in a data frame. Now we are defining that, okay, our time values are the, so here we are saying that, okay, we are saying that whatever time values we are saving it is in a data frame as time, and we are specifically mentioning that, okay, these are all the individual columns which we would like to save. So whenever you run this cell, it will save this Astropy table and the respective columns as a text file in the output directory, which we have just made here with the name data, which you can also see here. So the data file which contains time and the associated flux and flux values, or I mean the both kinds of flux values, are stored in this text file, light curve sector 18.txt. Now, as I said that we already know from literature that its period is 2.867 days, but we are also we would like to see whether like what is the period value we can get from the test data. And for eclipsing binary stars, you can also check whether the period is, I mean, you can also calculate the period values just from the light curve. And I am saying this so because you see these dips in these eclipses, these are kind of, they are periodic, and because they are periodic, you can just we can just you can just make a difference from these time events, and you can see what period you get from these when you subtract one time, like the mid time of this eclipse and the mid time of this eclipse event. And if you subtract these two quantities, you will get a period which will be which will correspond to this period. But in another case where the variability is not so, I mean, where in all other cases where the target is non-eclipsing, you cannot do that because you are not very sure like at what time the one star goes beyond the another star. So to find the periodicity in a light curve, we use a method which is known as the periodogram, and it is a commonly used statistical tool which we use for finding periodic signals in the data. It's somewhat similar to the Fourier transform, but the condition in Fourier transform is that your data should be evenly spaced. But in astronomy and in real world, you cannot observe a single target for a longer duration of time. And the reason is because it's almost next to impossible to observe a single target for a longer duration, and that too 24 hours in a single day. So the reason being because it's very hard to operate telescope on if the weather is really bad. So for example, if there are clouds, rain, high humidity, high winds, you cannot operate the telescope on those occasions. The second thing is that because the Earth is orbiting around the sun, so our objects, they might not be visible during a certain seasons. The third point should be that telescope might be busy with another observations, or there might be some maintenance or any kind of associated overhead time with the telescope. And another thing is that it is really extremely expensive and difficult also to observe a single target constantly. So that being said, our data, it cannot be observed constantly. So whenever I'm saying that we have data points, so it's not like that I do have evenly spaced data points. Even in case of test data set, you see there is a so TESS is, because TESS is the space-based telescope, so it can observe a single target for 27.5 days. It's the duration of the one sector in which TESS observe a single target. But then again, when it shifts to another target, then it cannot observe the same target, right? So even in the test data set, we have the data gap, and we also have this data gap, which is, so this is the downtime. So this is the time which TESS takes to send data back to the Earth. So it cannot operate between, it doesn't operate between these. I mean, there is always a gap between one sector data. So that being said, we use this Lomskargel periodogram technique to search for these periodicity in the unevenly spaced data. And in case of input, we need a time series data, time and associated brightness or magnitude. And how this works? So it checks for different frequencies, and it checks whether that particular frequency, it fits the data or not. And when the I mean, it's somewhat similar to Fourier transform, because in Fourier transform also we go from time space to frequency space. So it's somewhat similar to that, but there is a extra factor which due to which we make sure that it takes into account the uneven sampling. Now, the output of this Lomskargel periodogram is the another data set in which we have frequency in the as the x values and the power as the y values. And it might be very accurate to say that the taller the peak, the stronger would be the chances that it is the frequency is repeating, and that's why you are getting more signal in that particular frequency. So for now, we will use the Lomskargel function of the Astropy time series function, and we will provide the time values, then the PDC set flux values, and its associated error values. And we will make a data frame containing frequency and power, and we will just use this auto power function inside Lumskargel. And the only keyword which we have provided here is that Nyquist factor 1. So the Nyquist factor 1 is the Nyquist factor equal to 1 means that it's the maximum frequency which can be calculated using this data set. And the maximum frequency, it depends on the cadence between the data points. So with the test data with 120-second cadence, we can go the Nyquist frequency or the maximum frequency is the 360 cycles per day. So now we have the Lumskargel power spectrum with us, which we can just plot using the normal matplotlib using the using the normal matplotlib value, functions, and see we have frequency here on the x-axis and the power. And you see the amplitude of this peak at almost 0.35. It's somewhat slightly larger than the peak at 0.7 or something. So you can also print this value, like if you're interested in saying the exact value of this frequency, so you can define value. So it says that, okay, we are using NumPy here, and we are saying that, okay, we are interested in that frequency which has the maximum power. So the np.argument max, it takes care of that thing. And because the period is inversely proportional to frequency, so it's just the thing which we have written here, and we can print the best frequency and the best period. So now you see that the best frequency is 0.3511 cycle per day, and the best period which we have got from the Lumskargel analysis is 2.8486 days. And as I said earlier, as I mentioned somewhere that, okay, as I've mentioned that it's the period of beta Persei is 2.867 days. And here we have got 2.8486, so which should be within the error, they represent the same periodic feature. Now you can do this exercise for the other sectors of this target, and here are some of the references which you can use for to understand the Lumskargel periodogram in detail. And these would be some exercise which I would like you to do. And these are some additional resources which you can go and see. So that's all from my side. And if there are any questions, you can just write down or ask me now. Yes, Aswin. I can't hear you.
Hi, Nikita.
Hi.
Yeah, is anyone speaking? I can hear.
No, I think Ashwin raised their hand and I asked him to ask the question, but I don't think if he's speaking or what.
Okay. Yeah, I also can't see any question in the chat.
Yeah, I don't see any question.
Okay, all right. So if there are no questions, I think we can wrap it up. Just a few announcements. We've shared the link to the capstone guideline project guideline last week, and we believe that participants have already started getting their data and are beginning the analysis. So please try as much as possible to get any data, whether in astronomy or any other field, to do your data analysis. The step-by-step on how you can do that in the capstone guidelines. So please do that as quickly as possible. By next week, we'll open up the capstone project submission link for those who have submitted. It's not it's going to last for at least 10 days when we open it up. So by this time next week, we'll open it up to the whole, for everyone to make submissions. And remember the rules. All your submissions must be in a Colab notebook. So while you work on your PC, to be advisable that you link up your notebook to Colab. And then if you make use of any data, do either make it away in such a way that data can be downloadable, or a link to download the data to notebook, because each of the notebooks will be run. So that's the announcement. Please, if you have any questions, do ask in the Slack channel. A number of questions have been asked today and yesterday have been addressed. The link to week 5 is in the channel, week 5 time series. You can just go to the channel and search for week 5 and you will find it there. Otherwise, it's also available in the GitHub repo. You see the folder week 5. So not sure we have any other questions for now. Otherwise, we can end. Okay, I can see Nikita, if you can see the question, there's a one there. Say, is the function Lumsky same as the fast Fourier transform?
Just a second. So what is the question?
Yeah, if you can look in the chat, it said by Topolilo, it said, is the function Lumsky same as the fast Fourier transform? And how to extract a period from a light curve?
Oh, so when I say that to extract a period from a light curve, so as I said that in case of eclipsing binaries, it is quite, I mean, you can visually see that there might be two repetitive dips in the light curve, and if you just take a difference between these two, the difference between these two dips, you can easily extract that feature, and that duration should correspond to the orbital period of the binary system. But I mean, you cannot use this visual analysis for those targets where you cannot see the eclipse. So in those cases, we use Lumsky periodogram, and it's and I think you were saying whether it's the same as the fast Fourier transform. It's not, because the fast Fourier transform considers that your data is evenly sampled. The evenly sampled means it should have data points which have been taken in a continuous manner, which, as I mentioned, that we cannot do that in astronomy. So it's better to use Lumsky for astronomical data sets. The second is, where can we find the required data if I want to perform a data analysis on gravitational lensing as was shown in today's presentation? Daniel, can you answer this? I think the Ogle data it should be somewhere on their website or somewhere, right? I mean, if it's not published, the gravitational lensing data.
Yeah, for gravitational lensing data, I think they do have it in the website somewhere.
Website. Yeah, it should be in their
Let
website.
me check just a moment. I think
Maybe, yeah, I can just.
someone did ask about this. So I'm sharing a link now in the chat. Yeah, so well, this is not my background, so just know that may not be able
Yeah.
to be a lot of help here. It means
Yeah.
I have to
Is
figure out how
this,
to get this.
did you
But
get the
I
link?
do believe that there are a couple of links, and I think there's a one here.
I think I found the
I'm just
link.
sharing two links right now. So
Is this the one which you have found? I have just,
I've just
okay.
replied to, is it Ashish?
Mm-hmm.
So I just checked the link
Ashutosh.
before we end this.
And there is
Call.
this another link of the Ogle website where you can access all the
Yeah, you can
data.
also search on Ugly. Yeah, they should also have maybe
Yeah.
some tutorials or Python guidelines on how to extract their data for
Hmm.
analysis. And for time series analysis in Python, I probably will suggest you check out Kaggle time series tutorials. You will see a number of them. That will be a good way to start because the time series we did here is basically just for astronomy. But not in this, even the hands-on that Nikita did is mostly for test light curve. Not sure if it works for, I know for things like X-ray, it's quite different. Maybe nicer new star data is
Yeah,
quite
I
different.
mean, it's
Gamma ray too.
if you want to extract any X-ray light curve, you should have a specific package which is known as high energy, high
So
HISOP.
in
It's
the
called what?
in the
High.
notebook there's also a link in the additional resources for the notebook 3. You will see a link for gamma pi for I think for gamma ray astronomy, and then there's one Stingray for Stingray is also used for X-ray. If you go to the link, you probably will see tutorials on how to fetch maybe any of the X-ray. But this you most probably will have a background in X-ray astronomy before you proceed, or you might have to take your time to do a lot of digging.
Yeah,
Otherwise,
because it's I mean it takes a lot of time to clean the X-ray data set. I mean, whether it's from XM Newton, your star or anything, but you can use the Lomscargle routine, which I presented here to find the periodicity in the data if you already have the light curve with you.
yeah, of course.
And
And
Daniel, here is a question for you. I mean, in the
yeah,
chat.
I'm looking at that. I'm thinking of doing a project
It's
with the CME velocity before it gets ejected using sharp data. Who should I contact? Oh, so I don't think that's the one I was responding to. You should just probably, what do you mean by CME velocity? I don't know what that means. Um, I'm not sure what you mean by CME velocity, Aswin. If you can elaborate, that's fine. Otherwise,
is it coronal mass ejection? Yeah, coronal mass ejection from the sun. Yeah.
oh, okay, I see.
Mhm.
Oh, okay.
But to be honest, I don't have any idea about
Yeah,
this
I'm not, it's not
solar
my,
data. Yeah.
yeah, it's not my area, but if it's time series data, what you'll probably do is to, okay, you have the data, good. If it's time series data, then what you probably do is, again, like I said, while you're trying to do a bit of hunting and analysis, you need to also have a background of what you're working on, or you need to spend some time to understand what you want to work on. What are the parameters in the data, and what are the things you want to predict, or what are the things that you want to infer from from the data?
Yeah, it
For time
also
series,
depends on the science goal, like which type of features do you expect from that data?
yeah,
I mean,
exactly.
is there any kind of variability there or what?
Yeah, I think for time
Hmm.
series, yeah, it probably might be things like
Hmm.
cycles and the rest of them, but it will probably be what the best thing I recommend is to read a few papers on it, and then at the same time for mostly for time machine learning time series, oftentimes is just to predict a feature, maybe to do more like forecasting for say the next, depending on the size of your data, the next month, 2 months, 3 months, 6 months, or 1 year. So there are
Oh,
you can check out
he's yeah, he's saying
Facebook Prophet. There's a Facebook package called Python package called Prophet. I think that's one of the easiest way to do machine learning. They do have very nice tutorial to do that, but you need to also understand the what's it called, the parameter that you want to predict. And again, do you need to do some feature extraction before you start doing your prediction? But it's also good to check out what other people have done. Okay, that's it. I'm not seeing any. So
Could you please share the link?
for the package you mentioned, sorry. You mean, I said Facebook Prophet. The name of it's just type Facebook Prophet.
Facebook and then what?
Yeah, just I'm typing it now.
Yeah,
Facebook.
okay. It will be better if you type.
Yeah, that's the name.
Okay.
Yeah, just type it on GitHub. It's a Python package for time series analysis. Yeah, machine learning time series is beautiful. It's robust and easy to use. You just need to load your data, whether in data frame and pandas, and then you're good to go. Yeah. Okay. But I think what you have to do is when you have the data, you may have to index the time. Remember, most times you need to for time series data. You can see it in one of the examples, I think in notebook, I think it's notebook 1 where you have to now change the time and make it an index. So I think that is what you need to do with your data in order to use Facebook Prophet. Yeah, so I think that's it. Thanks everyone. We're 2 hours at the dot. So thanks for joining us this evening. Please, if you have further questions, do ask in the Slack channel. You can kickstart your project, start writing your problem and your data description. Remember, all of these things count. And also possibly do further consultations, look at what other people have worked on, and then check out other examples. And then at the end of the day, you should be able to come up with something that is worth it. Okay, on this note, you guys should continue your reading. Please go through the notebook, check out the additional resource link that have been shared, ask questions in the Slack channel, consult Google as well. Google is your friend, another search engine. Yeah, and it will make your life easier. On that note, bye everyone.
Bye. Bye, everyone.